All right, guys, welcome back. We are going to go ahead and get started here since it's a little bit later today. I want to make sure that we have enough time to cover everything. We're continuing our discussion of BGP, and in this particular case, we are going to be discussing next, what we call NLRI origination, right? And this is basically just prefix origination that we're going to be taking a look at. We're going to talk about it. It stands for network layer reachability information. We're going to talk about specifically what network layer reachability information is. What are the ways that we can actually originate prefixes into BGP? So for example, could I use a network statement? Could I use redistribution or maybe some other method of origination? We'll talk about, towards the end of the lesson, what are some of the conditional advertisement options that we have, right? What is a conditional advertisement? How do conditional advertisements work? How does conditional route injection work? And so on. So we'll start by talking about what is NLRI in general, right? NLRI stands for Network Layer Reachability Information. In other words, a fancy term for a route. Or a prefix. We've seen up to this point that there are differences in BGP about how it does its advertisements based on what we've seen with like a standard IGP routing protocol. BGP does things a little bit differently than your standard IGP routing protocol. We've also seen that BGP doesn't know about the path. It only knows about the prefix information. Now, specifically, the way that BGP advertises is any kind of prefix or reachability information is with two different message types. We're going to take a look at these different message types in a packet capture. It's a pretty basic concept. We have a BGP update, which includes information about the prefix. And then we have a different type of update, which is what we call a BGP withdraw message. And both of these updates and withdrawal messages are used to exchange that network layer reachability information. Withdraw is basically a negative update in essence. A regular update is going to include things like the prefix length, the next hop value that's associated to that particular prefix, and all the different attributes that are also associated to that particular prefix. Now, there are many different ways, actually several different ways, to originate network layer reachability information into BGP. It can be done multiple ways, and we're going to take a look at each one of these from some very basic methods to some pretty advanced options. But one of the ways is going to be using the network statement. In the case of IGP protocols, this is different with regard to the network statement as opposed to what we would see in BGP. If you recall from previous discussions of our other IGP processes, including a network statement means that we are enabling the process to run on the interface, whichever interface is included in the range of that particular network statement. And then in addition, we're also allowing those included interfaces, whatever prefix is assigned to those interfaces, whatever routes assigned to those interfaces, those are going to then be in turn advertised into the routing process. With BGP, it's a little bit different, right? We activate the BGP application on the interface by using a neighbor statement, not a network statement, and then we issue the network statement to be able to originate prefix route or routes or network layer reachability information into BGP. All right. So it means that we're going to advertise the route, but here's the big difference, right? It means the network doesn't need to be directly connected to you in order for you to originate a route. All it has to do is exist in the BGP rib, and we're able to originate a route. That's a very big difference from what we see with our standard IGPs. So as long as there's a match in the routing table, all right, specifically the routing table, not the BGP rib, but the actual routing information base, the global rib. As long as there's a match based on the network statement that you configure in the routing table, then BGP can originate that prefix. There is a caveat to this though. In order for us to be able to use the network statement through BGP, that network statement has to match exactly what's listed in the routing table. So unlike an IGP process where I simply enable the routing protocol on the interfaces based on using wildcard masks or based on using some sort of classful network statement, which would then include multiple interfaces, with BGP, there has to be an exact route in the routing table in order for us to be able to originate that routing information into BGP. Now, there's some ways that we can handle this. There are ways that we can kind of make sure that this happens. We could create a null zero static route, for example, and then originate that into BGP with our network statement matching that null zero static route, or we could just simply make sure that the appropriate prefix exists in the routing table coming from some other process. Could be a static route that doesn't point to null zero. It could be through some sort of IGP routing process or whatever. Okay. There are many places you can do this as well. You could originate networks in the core of the network, or you could originate networks at the edge of the network. Remember, we're not trying to identify path information. We're trying to identify prefix information. So deciding where we're going to originate those prefixes, I wouldn't say it's necessarily an arbitrary choice, but it doesn't necessarily have to be a prefix that exists specifically on that particular router. It depends whether or not you just want a single point of control or whether you want to distribute the process across multiple devices. But here's the key, and this is the critical difference, is that the network statement needs to be an exact match of the route in the routing table. Sorry about that. In most practical cases, you would probably originate the networks at the edge. It's easier kind of from an administrative point of view to originate the networks at the edge of the network because again, we're going to be using our IGP process most likely to route within the domain. We just need to make sure that the prefixes are, that the network layer reachability information exists in the BGP rib, and then we'll recurse to those prefixes using our IGP routing process. So typically, if we're injecting routes, we're going to do that from the edge with those routers that are created, or those neighbor relationships that are being created through external peering relationships from other routers that are in different autonomous systems. Okay. In BGP, we do have another option. We can actually redistribute routes into BGP rather than using the network statement. There are a couple of caveats when we do decide to redistribute routes from BGP, from some sort of other routing process, like a static or connected route, or maybe through some IGP process, is that those routes will not include any OSPF external routes. I'll mention some more about this in a little bit more detail later on in this discussion, but it's basically really just a loop prevention method. Okay. We have two other methods as well. One of them is to use BGP aggregation. And then the other one, which is the last one we'll talk about in our lesson today, would be to use some sort of BGP route injection. We're going to spend a lot of time in future lessons talking about aggregation. There's a whole bunch of detail, and aggregation in BGP is way more flexible. We have a lot more options with aggregation in BGP than we do with route aggregation in, say, like EIGRP or OSPF. So we are going to spend some time talking about that in more detail in some of the future lessons. There are many different attributes that go along with the aggregation. There are many ways that we can actually perform the aggregation in BGP, and it can be a little bit complicated. All right, so we're going to have a much more detailed conversation about that later in a separate section in a different lesson. The key point for origination with the aggregate, and we'll take a look at all these, by the way, as in our configuration and our topology. So it may seem a little bit confusing jumping from one option to the next, but we'll take a look at all these and apply some of these concepts to our topology. But the key point for aggregation is its difference with the network statement and how we originate this reachability information. With BGP aggregation, we require at least one subnet that's going to be included as part of the aggregate to be in the BGP table first, where the network statement doesn't require the route to be in the BGP table, it requires the route to be in the RIB. So if I have some sort of connected network, but I'm not running necessarily BGP on that connected link, that connected link will not show up in the BGP RIB, but it will show up in the global RIB, and then I can execute a network statement to include that connected link, and then that would, in turn, of course, make it part of the BGP RIB. All right. It is something that we kind of normally assume, right? We normally assume that if the route is in the BGP table, it's probably in the global RIB, but that's not always going to be the case. All right. I don't know if I'll be able to demonstrate an example of where that wouldn't be the case, but it is just a clear distinction that you need to make. With an aggregate process, basically summarization within BGP, in order for us to create an aggregate, that route, there has to be at least some sort of prefix that's part of that aggregate inside the BGP RIB. All right. So we're going to talk specifically about the BGP network statement. I'm going to take a couple of notes here and make sure that I'll put these into the Google Drive for you guys. But we're going to break down some of these options. All right, so BGP network layer reachability information. And the first option that we have is the network statement. And as I mentioned before, this network statement has to be an exact match, must be an exact match for a prefix in the global RIB. All right. So I'm going to put some notes here for aggregate as well, and some of the other options that we're going to see throughout the rest of the lesson here. But let's focus on the network statement first, because that's quite frankly going to be one of the more common methods that you're going to use to inject reachability information into BGP. All right. When we originate a prefix, we're going to send the prefix into BGP with an origin code of IGP, which, by the way, is a little I. All right, we'll take a look at this in the BGP table later on. So whenever I originate a route, what we call local origination, based on the network statement, that's always going to show up with an origin code of IGP. We're going to see, we talked about this in one of our previous lessons, we'll see it again in our next lesson actually, that the origin code is used as part of that best path selection process, and we're always going to prefer routes originated with the network statement as opposed to routes that originated with, say, aggregation. So we will prefer, sorry about that, we'll prefer routes locally originated using the network statement versus some other method. And one of those other methods could be aggregation, which we'll see next. Okay, and that just basically is, I mean, there's nothing special about that concept. It's just part of the BGP path selection process. All right. Now, as I mentioned before, it does require an exact match in the global RIB in order for us to be able to originate that prefix. It does not have to be connected, by the way. It could be a route that's learned via IGP. It could be a route that you've configured statically. But regardless, it has to be an exact match. And I'm talking about the prefix itself plus the prefix length. If we're issuing the network statement without the mask keyword, so the syntax would be something like this. Under the BGP process, so config-router, we would put in network. We'll just say 1.1.1.1 mask 255. So we're not using an inverse mask in this case. We're using a regular dotted decimal mask. But that mask keyword needs to be there. Now, if you decide that you don't put the mask keyword in there, okay, BGP is going to basically assume that you're talking about a classful network. All right. So if I was to say, for example, network 1.1.1.0 and then hit the carriage return, this would actually be accepted, but it would be assumed as 1.0.0.0 because 1 is a classful Class A network, and the classful representation of that Class A network is 1.0.0.0. Okay. Make sure in this case that you pretty much err on the side of caution. Use the mask regardless of how you're injecting the network. And if it's not needed, BGP will simply ignore it. If it is needed, of course, then you're going to be working correctly. Okay? Another key point is that when we originate a prefix using the network statement, all right, network originated prefixes, well, that's what we're talking about here in this case, so I'm just going to put it in here. We are going to originate these prefixes with a weight of 32,768. We talked about the weight attribute previously in one of our previous lessons, and we'll hit it up again in the next lesson as well. But weight is one of those attributes that's always going to be considered when I'm doing a route, when I'm doing my selection process. All right, and we do this because we want to prefer routes that I originate, self-originated, prefer self-originated over other routes, meaning other routes that are coming in from other peers. Okay? So we're going to originate these prefixes with a weight of 32,768. The higher the number, the more preferred the prefix. And we'll see this in our BGP table as well for those routes that we originate. Now we do have BGP pre-configured here. I went through and made sure everything was working this time and everything is up and running. We're going to add an additional link in this topology for part of our final discussion, but we're running router 4 as a route reflector, router 2, router 1, and router 3, and router 5 are route reflector clients to router 4. In AS100, we're running EIGRP 100 as our internal IGP process, and we're including all the loopbacks as part of that BGP routing process. Those are being originated, by the way, by the edge routers, router 1 and router 5. And then we have some eBGP peering relationships between router 7 and router 8. So this is the same topology that we've been using for all of our other discussions. Okay? What we're going to do is we're going to go ahead and set up our packet captures on router 4. We'll use Wireshark and just simply capture. It doesn't really matter what interface we capture on because we're going to see the updates and the withdrawals regardless of the interface. But we'll do a packet capture over to router 2. That would probably be the best option. And what I want to show you is how do we originate some of these prefixes? What's the difference between them? We already know what the transport profile is for BGP, and that's that it uses TCP port 179. So we're just going to create a packet capture and we're going to look for captures based on that. Remember, we don't really necessarily know in advance who's the client and who's the server. So when I'm matching the flows, I'm going to look in both directions for TCP. Okay? So if we go into router 4 and just kind of take a look at what our standard configuration is. we'll come in here and do a show IP or show run pipe section BGP. We're just doing our basic configuration. We can see we have BGP peers configured with router 1, router 2, router 3, and router 5. They're configured as route reflector clients, so we don't have to have an IBGP full mesh configured, but the end result is the same. Prefixes are going to be advertised. If I do a show IP BGP all right, sorry about that. I was missing a configuration here, but actually we can see here based on 4444 some of the information that I've already provided you. The next top attribute is quad 0, which indicates that this is a self-originated route, and we can see that the weight is 32768 as I described. But I am seeing the other prefixes here, the other loopback interfaces here. And what I want to do actually, show run pipe section BGP, is I want to remove that redistribute connected from router 4 because I want to originate this route in a different way. So let's go into router BGP 100, and we're going to do a no redistribute connected route map loop. But we still should see show IP BGP summary. We're getting the prefixes from the other routers. All right. So what I'm going to do is I'm going to go ahead and create a packet capture in Wireshark. We're going to go ahead and capture this on the link going over to router 2. And what I want to do in this case is I want to create a filter that filters specifically on BGP port 179 as the source port and as the destination port. TCP, sorry, not BGP port, TCP port 179, just so I can make sure that I'm just capturing that information and not some other erroneous information that we don't really need to see. So let's go ahead and allow a couple of captures here. And let's go into one of these datagrams. We need a TCP packet here. There's a TCP packet. And I'm just going to create a filter that says source port, apply filter selected. I'll change that to 179. And I will also do destination port, apply filter, and selected. And we'll also change that to TCP 179. Didn't want to do that. Let me try that again. I want to do an or, sorry, not and. We won't match anything on that. So apply filter or selected 179. Okay. So we're seeing essentially all the messages going back and forth between the BGP peers. These are just our basic keep alive messages. So now what I want to do is I want to originate the loopback on router 4 into BGP, and we are going to do that with a network statement. So I'm going to go into router BGP. The first thing I probably want to check though is I want to do a show IP route 4.4.4.4/32. Make sure I have a route for that particular prefix. I could, of course, look at my routing table as well. There's lots of ways to verify whether or not you have route information. But depending on the size of the routing table, you may want to use a particular method that might get you to the result a little bit quicker. So I'm going to go router BGP 100, and I'm going to originate this route into BGP by using the network statement, which is the first option. So if I do a show IP BGP, we can actually see that we're still originating that route. Nothing really changed other than this information at the end here, which indicates that's the origin code. I know it says path here. This is a little bit of a formatting problem. Well, it's not really a formatting problem. These aren't prefixes that we're learning from other routers, so we don't really have a path per se, because we're not learning any external routes at this point. Router 7 and router 8 aren't originating any information, so we would see AS path information there if we had path information to show. But the origin code here indicates that this is internal. All right. Actually, I should specify IGP. Internal would be that would show up over here. So this represents internal, this represents IGP. So we can see that this route is being originated It says that the originator of the prefix, if I do a show, show IP BGP 4.4.4.4, we see that the originator is quad 0, which indicates that I'm the originator of the route. The origin is IGP because we originated the prefix with the network statement. And we, by the way, automatically copy the BGP med, that multi-exit discriminator value, into the attribute, into the update, indicating a metric of 0. We wouldn't have really a metric in this case because it's a connected route. But notice that we have a weight of 32,768, and we also identify that this is a local route, meaning that it's locally originated. All right. So now let's take a look at the format of the network layer reachability information in our Wireshark capture. Specifically, I'm looking for an update which would have come out to indicate that the route was being updated. We're seeing this update going from 4444 to 1111 and 444 to 2222. Let's just take a look at this one here. And we can see that this is in fact standard BGP. Destination port is 179. The source port is 41178. Now actually, I should see a different update here. And let me see if I see it here. No, same thing there. Whether or not it's going to be the source port of 179 or whether or not it's going to be a destination port of 179 is kind of irrelevant in this particular case. It just identifies who is the client and who is the server in the transaction. So because I'm sending the data to port 179, that would indicate that in the TCP negotiation that this router became the client rather than the server, right? So that has nothing really to do with how updates get propagated or how they're sent. It really just has to do with the fact that this particular router is not the TCP server, it's the TCP client. All right, and that's actually why I decided to do the filter in both directions, because if I was filtering based on source port of or destination port of 179, source port of 179, assuming this router would be the server, I would not have seen this information. So we always try to match in both directions, since you don't really know who's going to be the client and who's going to be the server. So inside the update, we see pretty much all of the network layer reachability information. We have the prefix information. Let me go ahead and close my TCP section here. We can see that this is an update message. It has a type code of 2. And we should be able to see all of the attributes for this particular prefix. So that's the prefix that's being advertised. This is the prefix length. That's the prefix itself. And then we see all the attributes that are included in this particular advertisement. Notice here we see withdrawn routes as well. And that's the distinction I want to make. We don't send a separate message to withdrawal routes. We use an update that includes a withdrawal message, which then would identify whether or not we're withdrawing the route itself. So we can look at the different attributes here. The nice thing about this is the flags also identify the type of attribute this is, right? This is a transitive attribute, which means it would be propagated to other peers. It's a well-known attribute, and so on. We talked a little bit about that in our section where we discussed the different attributes. AS path is empty in this case because we're originating this within the autonomous system. The path attribute, the next hop attribute, again, type code for this attribute is a 3. The length is 32 bits, which is 4 bytes, and the next hop value is 4.4.4.4. This is a transitive, well-known attribute as well. And then we have our multi-exit discriminator. That's also a 32-bit attribute. The multi-exit discriminator is type code 4, and so on. So you can see pretty much a lot of these different attributes have similar characteristics, right? This particular attribute is only one byte, not 4 bytes, so it's only 8 bits, and the origin code is 0, which indicates this is IGP. I doubt that they would get into the details of understanding the different type codes for the different attributes, but as long as you can look at a capture and you understand what's happening and what these attributes are used for, how they're used in the path selection process and the algorithm, that's the most important part, right? That's the part that we want to make sure that we understand. So this is really just what network layer reachability information is. It's the information about the prefix. It is provides the attributes that are included. Some of these we could suppress, some of these we can modify. We'll talk about that a little bit later on. But that's my update message. All right. Now, if I go ahead and shut down that port, I should see the route being withdrawn because I don't have a match in the routing table. There may be a couple of ways of doing this. Hopefully I'll be able to capture this because we're going to lose our peering relationships based on the fact that we're peering to this loopback. But let me see if I can go ahead and go into interface loopback 0 and shut down that port real quick. We'll let it process, and then we'll do a no shut. And what we should see in the capture is we should see an update message come out indicating that this particular route is being withdrawn. So let me see if this is the right one. Yes, we are seeing that right here. So this is what the withdrawal looks like. It's an update message, type code of 2, and the withdrawal route's length is 5 bytes. And that's because we're representing a couple of different things. We're representing the prefix length, and we're representing the prefix itself. And basically, it's just a message that says, hey, let's go ahead and remove this route. Like I said, technically, there's really no difference between an update or withdraw in BGP. It uses the actual update message, but it just gives us the route that we need to withdraw. So it's a pretty basic message. We don't care about the attributes because we're removing the route anyway. Okay. So, and then I would have seen the update come in as well, indicating that the route is back. This looks kind of interesting to me. Update, update, update. Okay. So yeah, this is where we were withdrawing additional prefixes because we lost our adjacency with the peer, based on the fact that we were peering with that loopback. BGP is smart enough to say, you know what, if I'm peering with the loopback and that loopback interface goes down, I know that I'm not going to be able to receive prefixes from these peers, so I'm going to withdraw those prefixes as well. And this also happens to be because we're a route reflector and we're reflecting this information to the rest of the domain. So it's interesting that we actually see it 1, 3, and 5, and then we also see 2 separately, and then we see the individual physical links. Again, this just happens to be because we're withdrawing the information based on the fact that we're configured as a route reflector. Okay. Now, one of the other options that we have is to use a BGP redistribution statement. So rather than using a network statement, we're going to use a redistribution statement. One of the key differences between the network statement and BGP redistribution, let me go ahead and go to my notes here. Let's do BGP, let's do redistribution. One of the key differences here is that the origin code is going to be a question mark. All right. In the network statement, we used an origin code of I to indicate that that's how we were learning that prefix. But in this particular case, we're going to use an origin code of incomplete. Incomplete. And that would mean that we would have a code of question mark. All right. And we'll see that actually. We're going to go ahead and implement this, and we'll see that in a little bit. All right. This is just indicated as an origin of incomplete. That means that from a path selection standpoint, or from a path selection point of view, the BGP process is going to choose the path that comes from the network statement versus a redistribution based on the standard BGP path selection process. When we do redistribution, if auto summarization is enabled, remember auto summarization is typically a feature of a distance vector routing protocol. But in the case of BGP, it actually does tend to act a little bit like a distance vector routing protocol. So we do have the option of doing things like auto summary and things like that. So we're going to go ahead and do that, turn that on. I'll show you how that behaves. Auto summary is not something that we would typically use in a modern protocol because we don't typically see that we have any kind of prefixes that, or we don't get assigned prefixes that are classful these days. We're using classless prefixes, but we'll take a look at this, all right? By the way, the auto summary command does not affect network statements. It only affects the redistribution process, and it would only apply to the redistribution process. All right, so let's go back to router 4. And actually, let me make a note of that. Auto summary could be enabled under the BGP process, and aggregates, I can't type today, would be advertised as classful. Okay? This does not affect NLRI with the network statement. All right, so I'm going to show you guys how this works here. Let's go back to router 4. Do a show run pipe section BGP. We're going to take out the network statement in this case, and we are going to redistribute the connected routes instead. So let's go and do no network. Oops, let's go into interface, sorry, router BGP 100. Router BGP 100. And we're going to do a no network. All right. And we're going to do a redistribute connected route map loop. So we're going to send this route in using the redistribution process. I could just do a redistribute connected, but that's going to include some of my physical links. But let's go ahead and also enable the auto summary command. All right. And I'll do a clear IP BGP just to make sure that we've got everything relearned. All right. So if I do a show IP BGP, pipe include 0.0.0.0, I should see the 4 prefix being originated. So it's, even though it is 4.4.4.4, we're the originator of the route. 32.768 applies, but now the origin code is what we call incomplete. Not sure why they ever called it that, but that's what it's being sent in as. We can also see that we're originating this particular aggregate classfully. All right, actually not aggregate, redistribution classfully. It's not normal behavior, but with auto summary turned on, obviously that's going to be the case. In most cases, like I said, we don't auto summarize because we're not going to end up getting classful subnets. So we're going to assume that for the most part this is off, but you may run into that on the test, and it may end up resulting in some suboptimal routing or routing issues in general. So we do want to make sure that the automatic summarization process is disabled. We can see this for BGP 100. We should see somewhere in here, yeah, right here, automatic route summarization is enabled for BGP. So we'll do a no auto summary, and we'll do a clear IP BGP star out, and do show IP BGP pipe include quad 0. And what I should see now is the /32 prefix. All right, so everything else is pretty much the same. If I do a show IP BGP 4.4.4.4/32, I'm still originating the med. The local preference is still 100. The weight is 32,768. Notice what we missed is we're missing now local, where we see sourced instead of local, but the origin is still quad 0, indicating that this is a route that I'm originating. And also we would see, again, the metric value here. Now that might be different, right? And we'll talk a little bit about the med itself. Med is actually kind of a finicky attribute. The med here would be different depending on how we're advertising the individual prefixes. But in the case of med, it's kind of one of those finicky attributes because and for that reason, for most practical cases, it's not going to be used. There's a lot of disagreement as to how med should be used based on the vendor, based on the code itself, or the versions of code. So that's something to keep in mind when you're dealing with the med value. Okay. Also, with the redistribution process, we are not going to include OSPF external prefixes. Let me make a note. OSPF external prefixes would not be included, even if they're part of the redistribution command. So let's say I do redistribute OSPF rather than doing a redistribute connected. All my O routes, my OA routes will be included, but not my OSPF external routes, which would be OE1, OE2, ON1, and ON2. All right, like I said, this is mostly a protection mechanism. The idea here, of course, is that you're redistributing BGP into OSPF. OSPF would ultimately identify those routes as external, and then if you redistribute OSPF back into BGP, it shouldn't really take them because those routes probably came from BGP in the first place. It's possible. Of course, we do have other routes that are possible, external routes that are possible. They don't have to be from OSPF. But again, just keep in mind, with the redistribution, OSPF external prefixes are not going to be included by default. We can actually override this behavior by going into the config-router, which is the OSPF process, and using the command redistribute OSPF, we'll just call it 10, match internal and external. All right, this would actually be include those external routes in the redistribution process. So you might run into a situation on a lab where you see something like this, where you're doing some sort of redistribution from OSPF, but by default, those external routes are not going to be redistributed, and those external routes might be originated from some other redistribution process into OSPF. And you have to fix it by making sure that you match internal and external. Okay. Just like before, we're going to set the weight to 32,768. That's going to make it more preferred. I think I forgot. Yeah. Let's go ahead and copy this because basically it's the same for these guys here. All right. And everything else is pretty much the same, right? The only difference is we would be identifying these as incomplete routes rather than internal IGP routes, okay? There is a problem in the opposite direction as well. If I'm doing BGP redistribution from an internal process, when I redistribute routes, when I redistribute BGP into an IGP, like say redistribute BGP 100 into OSPF or BGP 100 into EIGRP, I'm only going to take the external routes. I'm not going to actually send in the internal routes. Same kind of idea here, right? We're talking about within our autonomous system, I'm not going to take the internal routes because those routes should already probably be a part of my IGP routing process for my transport, my reachability. And if I go ahead and redistribute those internal routes back into our IGP process, again, we could see some pretty crazy stuff happening. We can override that behavior. If I go into, for example, router BGP, we're not doing that redistribution here, but let's say I go into router BGP 100 and I say BGP question mark. There's a command that we can use called redistribute internal, all right, which allows the redistribution of iBGP routes. But look what it says at the end here. Dangerous, danger, danger, right? It says it's dangerous because we can create a loop and we can crash the router. There are cases where it might be necessary for us to do this. Probably the best use case would be a layer 3 MPLS VPN. But again, we probably would avoid doing this by doing some other sort of distribution of the routes between the ISP, the PE router, and the CE router. Okay. All right. Now the next one. So both of those are pretty straightforward. Redistribution and doing a network statement. The next option that we have is a little bit more interesting, and it's kind of a little bit more complicated. We have two more options to discuss here. This one's going to take a little bit longer because there's some stuff that we're going to be working with in this case that you guys probably aren't familiar with. You're probably familiar with the two that we talked about previously. And it's what we call BGP conditional advertisements. All right. Now with BGP conditional advertisements, we create something called an advertise map based on an exist map or a non-exist map. And what that's saying is that I have to meet certain conditions in order to originate the network advertisement or to not originate the network advertisement. And I would actually use the neighbor command. And this one we definitely have to demonstrate because it's kind of confusing. Advertise map. Even the documentation is a little bit confusing on this one. Non-exist map to, or I could do possibly an exist map. By the way, the map to is just a name, but we're going to take a look at a configuration example here. The logic is essentially this. I'm going to match some prefix in an advertise map. Now, if the prefix is matched in the non-exist map, that means it doesn't exist. Or if the prefix is matched in the exist map, it does exist. Now, if the prefix is true or the prefix does exist, then we're going to originate what's in the advertise map. We can also do the opposite logic of that to say that if the prefix is not in the BGP table, then I will advertise what's in the advertise map or the non-exist map. You can see where this can be a little bit confusing. All right. It's an interesting feature in a use case for when we're doing redundancy designs. Like if a link goes down, it doesn't exist in the BGP table, then you may decide to do some sort of origination based on that information. All right, so let's go over to our topology here. We're going to look at router, this now from the perspective of two different routers, router 5 and router 7. So let me go ahead and stop my capture because we're not going to be looking at that anymore. We're going to be looking at this from the perspective of router 5 and router 7. So if I go into router 5 and I do a show IP BGP summary, we can see that we have a neighbor relationship. It's idle. Okay, well we have to fix that. Show run pipe section BGP. We don't want to be in an idle state here. 57.7 remote AS51 show IP interface brief. Link is up. So let's go to router 7 show run pipe section BGP. I'm guessing I don't have it configured on this side. Yeah. No neighbor. So config T. Why is that guy in BGP 100? Let's get rid of that. No router. Ah, I know why. I broke my routing here because I did redistribute connected route map loop, and it overwrote the previous BGP process. I think. Let me see. I'm not really concerned about router 8 in this case. Let's just get rid of BGP, no router, BGP 100, and let's fix router 7. Okay, so router BGP 51, neighbor 172.16.57.5, remote AS 100. All right. And we should get a peering relationship. There we go. And let's also go ahead and just do router BGP 151. Network 7.7.7.7, mask 255, 255, 255, 255. But if I do a show IP BGP, I'm getting those external prefixes, including 5.5.5.5, which is going to be our focus. And notice that we are identifying these as incomplete as they come in. All right. And actually, that should not be the case. Yeah, that's fine. Actually, we are getting the AS path of 100, which means these are coming from autonomous system, BGP autonomous system 100. From router 5. Okay, so if I do a show IP BGP summary, which is what I wanted to see before, I can see actually in router 5, show IP BGP summary, I can see that I have a peering relationship over a primary connection, 57.7, and I'm receiving a prefix from that particular router. Now let's say that we end up having multiple peering relationships. This is going to be an interesting discussion. I think you guys will find this to be very useful. But let's say that I go ahead and I have multiple peerings. So we're going to go to our topology, and we are going to create now an additional connection here. I'm just going to throw in a switch, and we're going to set up, we'll just call this backup. All right, and I'm going to set up a link on, let's do gig 03, and on this guy gig 03. All right, and this network is going to be 75. All right, keep these in line here because we're going to be manipulating some of these values here. So I'm going to go to router 5, config T, interface gig 03, no shut, IP address 172.16.75.5, and router BGP 100, neighbor 172.16.75.7, remote AS 51. All right, same thing on router 7. Interface gig 03, no shut, IP address 172.16.75.7, and router BGP 51, neighbor 172.16.75.5, remote AS 100. So I should get a peering relationship between those two routers. Show IP BGP, oops, summary. And you can see here now that I've established essentially 2 links to the peer. I've got 2 TCP sessions, and I can exchange reachability information both of those ways. Now if I go over to router 7 and I do a show IP BGP 5.5.5.5, you'll see here that I have from router 7's perspective, multiple paths to the destination because I have multiple peerings. And I can reach the 5.5.5.5 prefix either through 75.5 or through 57.5. And if you look, pretty much everything here is the same. They're both valid. But if I do a show IP route to 5.5.5.5, you can see that I'm actually using the 57 link as opposed to the 75 link. And that's based on the actual best path selection algorithm. We can't load balance, even though these links look basically the same, because BGP doesn't do that automatically. It's going to have to decide which path to use, one path or the other. Now, there could be a potential issue here based on where we want the traffic to be received. Let's say that we want to use the original link. We want to influence the inbound traffic flow, which means we need to apply an outbound policy. Remember, in BGP, outbound policies affect inbound traffic flows. Inbound policies affect outbound traffic flows. So let's do something on router 5 here. And let's do, this doesn't really have to do with what we're talking about, but we'll get there eventually because we're talking about this conditional matching, right? So let's create a route map. And we'll call it prepend. We're just going to do an AS path prepend. Set AS path, prepend, and we're just going to prepend 100 4 times. Okay? And then we're going to go into router BGP 100. And for the neighbor of 172.16.75.7, we're going to apply the route map prepend out. Okay? Do a clear IP BGP star. So that's going to send a triggered update over to router 7. And then if I go back over to router 7 and I look at show IP BGP, let's do a show IP BGP for 5.5.5.5. It should be there. Oh, /32, sorry. Oh, why is it not there? Show IP. The neighbor is up. Show IP BGP summary. We're not getting a prefix. Let me do a clear IP BGP star. We definitely should be getting the prefix. Oops, didn't want to do that again. Let me make sure what we did should not have affected the primary link. Update source loopback 0. 75.5 prepend out. So permit, prepend, set AS path prepend 100, 100, 100, 100. There we go. I guess I just didn't give it enough time. Show IP BGP for 5.5.5.5. And we can see here in this particular case, before we were, well, we were choosing 57 before anyway, but in this case, we're definitely not going to choose 57, which was our primary link, by the way. Because of the path. And actually, I wanted to apply this to the other. Well, actually, no, this is exactly what I wanted to do. My point is that I'm trying to influence how router 7 decides to reach the destination. Okay? And by changing one of the attributes of the relationship based on the relationship that I have with the peer, I'm able to essentially influence, well, conceivably influence how router 7 decides it's going to route back over to 5.5.5.5. If I do a trace to 5.5.5.5, I can see I'm using the 57 link. I was before anyway. Let's just assume that we weren't, right? That's not really the whole point though, right? Router 5 is trying to adjust an outbound policy by saying the return traffic should use that link, the 57 link, over the 75 link. All right, now one interesting thing that we run into with BGP is that even though we think we have full control, we don't. We have full control about how traffic leaves the network, but we do not have control about how traffic returns to the network. So we're doing an AS path prepend to influence how R7 sends its traffic back to R5. All right, but since this direction is out of R5's control, there's nothing to say that R7 couldn't do something like manipulate the values on its side. So let's go into R7. And what we're going to do in R7 is we're going to influence path selection by preferring the 75 path. All right. Let me think how I want to do this. Let's do, we don't need to do a route map. Let's just go into BGP, because I mean this would end up applying to being applied to all the prefixes, but that's okay. We don't really care. And I'm going to say neighbor 172.16.75.5, and I'm going to specify a weight of 1,000. All right. And if I do a clear IP BGP star in, what I'm essentially saying is let's go ahead and refresh those prefixes that we're learning from that peer. And if I do a show IP BGP 5.5.5.5, we can see that the best path in this case is being chosen as the one with the longest AS path. So if I do a trace now to 172, or excuse me, to 5.5.5.5, I'm now using the 75 path. So even though router 5 said, hey, this has a longer AS path, hopefully that's going to be one of your primary decision factors, and so you're going to decide to route to me over 57 rather than 75. Router 7 said, you know what, I can control how I leave my autonomous system, and I'm going to do that by using the weight attribute. Okay? None of that really has anything to do with what we're talking about now, except how do we get around this, right? And you know, we even though the AS path is longer, we're weighting it higher locally. That means that ends up being the best path. So, in other words, we really don't have control on how traffic returns. We only have control on how traffic leaves the autonomous system. This is specifically what conditional advertisements are supposed to assist with, and that's why we talk about it. Okay. Router 7 can only choose one path or the other because it knows about both paths. It's learning that prefix from both sides. So it's not really, you know, it can make a decision because it knows that there's a decision to be made, I guess is what I'm trying to say. All right. But what if we were able to override the process and say, you know what? Don't advertise it in that direction, unless the other path is down. So unless R7 is doing some sort of like static routing, we should be able to control the packet flow because we're only advertising the route on one particular path. That's where conditional advertisement comes in. All right. Now this gets a little confusing. The documentation itself is not very easy to find as well. There is some documentation out there on this configuration, but I'm going to go ahead and put this into our notepad and try to describe this conditional process that we're going to be doing here. All right. So eventually we're going to be under, let me just do a configuration example based on our topology. We're obviously going to be in router BGP 100 because we're going to be configuring this on router 5 going over to router 7. All right. Now, the first thing we need to make sure of is that and this is one of the downsides to this process, is we need to make sure that the connected link is part of the BGP process. And that's because we're matching conditions based on the BGP table, the BGP rib, not the global rib. That's a very, very important concept when we talk about this conditional matching. So we're going to go ahead and put in a network of 172.16.57.0 with a mask of 255.255.255.0. And we actually need to make sure that nobody else is originating that route. So let me go to R5 and do a show IP BGP 172.16.57.0. It's not in the table. All right. So we're not originating, we're not getting that route from somewhere else. It's already not in the BGP table. So we need to make sure that that's in there. I'll explain why that is in a little bit. Okay. I need to make sure that I'm the only one that's originating this prefix, because otherwise this conditional matching won't work. What we're going to do is we're going to be conditionally advertising information out to a specific neighbor. All right. That's different than, say, between other neighbors based on, other attributes that we want to influence for other specific neighbors. All right. So we'll take a look at this configuration. We'll go step by step here, and I'll kind of try to break this down piece by piece for you guys. All right. Remember what I'm trying to accomplish here. I'm trying to say that I want all my traffic to come into my original path, which is the 57 link, not the 75 link. I want all my traffic to come into my original path. I don't want to use the other path unless the peering is down on that original link. All right. We will apply it on the link, this particular condition. We're going to apply this on the link that we don't want to use. All right, so let me kind of go through, kind of put all the configurations in here, and then I will go back and explain what each of these conditions are and why we're using these. All right, so we're going to say neighbor, and in this case, we want to apply this. I got to keep this straight in my head here. 172.16.75.7. All right, and we're going to use an advertise map, and let's just call it advertise 1 in this case. Non-exist map, and we'll reference that as non-exist. I'll put all the names in uppercase so it's easy to kind of pick out. All right, so that's the actual command. That's the way we apply this conditional advertisement to the peer. But we also have a bunch of other configurations that we have to apply. So we have to create a route map called AVD1, permit 10. And we are going to match, in this case, a prefix list, IP address prefix dash list. And let's just call this PLADV-1. All right. Which means we also have to create a prefix list. IP prefix list, prefix dash list, PLADV1, and we're going to say permit 5.5.5.5/32. That's going to end up being the prefix that we want to be able to advertise. Now we need to create another route map called the non-exist route map. And again, I'll go back and kind of break this all down for you guys as part of the process here. Like I said, it can be very confusing when you're setting this up, but it's kind of a recursive configuration here. Match IP address prefix dash list, PL non-exist -1, and we're going to create a prefix list here. IP prefix dash list, PL non-exist exist -1 permit, and in this case we're going to be matching against the prefix or the primary link, if you will. So that's going to be our 172.16.57.0/24. Okay. So let's kind of walk through the configuration here a little bit, and then what I'm going to do is demonstrate this, and we'll go through the example, and then we'll be wrapping up pretty soon here. But all right. So regardless of how we decide to do this, we could do this based on an exist map or a non-exist map. In our case, we want to do it based on a non-exist map because we're saying, hey, if the primary link is not available, then you can go ahead and advertise this prefix over the secondary link. But if the primary link is available, then I don't want you to advertise this prefix over the secondary link. Okay? So what we're checking is the exist or non-exist. We're talking about the BGP rib, not the rib. And in other words, the BGP table, not the global routing table. So we are conditionally matching against what we need to originate into BGP first, which means it has to exist in BGP. We could use a static route tied to enhanced object tracking if we want. This process is not ideal. It's not very fast, but there's many ways we could do it. The idea, though, is that whatever we're matching against has to exist in the BGP table in order for us to be able to make a decision. All right? We'll shut down the link to simulate that failure, but remember, just because the link is available doesn't mean that the destination is reachable. And that's where you might decide that you want to do some alternate, like IPSLA object tracking or something like that. Okay? So let's go ahead and put this into our configuration. Before I do that, let's do a show IP BGP neighbor 172.16.57.7 advertise routes, and I want to include 5.5.5.5/32. All right, so I'm sending it over the 57 link, and I'm sending it over the 75 link. I'm checking this because I may have mistyped some addresses and stuff before I paste this configuration in. What should happen is once I put this configuration in, is it should stop sending this prefix over the 75 link, if I did this correctly. All right, so let's go ahead and put this into our configuration. Config T. All right, hey, that's good. That worked. So now let's see, it should be still going over 57, but it's not going over 75. All right, whew, that worked. I'm actually kind of surprised because there's a lot of pieces here, but I took good notes. So here's what I'm saying. I'm saying, okay, for this peer, I'm going to advertise prefixes to this peer based on this advertised map, which is going to match against this non-exist map in my as a condition, as a match condition. All right, and this is the prefix that I'm going to advertise based on the map that I've created. So the prefix list is referencing this particular prefix. So this is kind of what I'm going to advertise to the peer based on this condition. And like I said, you can do this based on an exist map, or you can do it based on a non-exist map. You could say, hey, if this prefix exists in the BGP table, then I'm going to go ahead and do this. If the prefix does not exist in the BGP table, then I'm not going to do this. So I'm saying route map non-exist 1, that's just the name. We're matching the prefix list PL non-exist. So I'm saying if this prefix does not exist in the BGP database, not the global routing table, but the BGP rib, then that's what's going to trigger this condition. Okay? So because this prefix exists in the global rib, then I am not advertising that prefix, the 5.5.5.5 prefix, over to router 7 over the 75 link. I can actually see this if I do a show IP BGP neighbor. And if I scroll down to the 57, the neighbor, let me see where that would be. A lot of information here. There's 57. I'm looking for 75 in this particular case, which would be the next one. Okay. We should see in here that condition check. 75.5. There it is, right here. So we can see condition map exists for this peer. The status is the 5.5.5.5 prefix is withdrawn. Okay? Or we're withdrawing prefixes for that particular, based on the map itself. All right? So what should happen then, if I go ahead and shut down the link, is that status should change. So we're going to shut down gig 02, and I'm going to do this on both sides. Interface gig 02, shut that down. I'll do the same thing on router 7. Interface gig 02, shut that down. And I should still have reachability. Let's just do that real quick. It might take a little bit. We're still waiting for convergence, but eventually that route should come back. But more importantly, what I should see for the neighbor, let's do this. Let's do, and show IP BGP neighbors include condition. Right, there we go. So now the status has changed to advertise because the link, the primary link went down, which means we're now able to advertise that prefix over the 75 link. It's a pretty interesting concept, right? Like I said, it's because the failure case, the link goes down, the state changed, not very quick to converge, but the set condition is not met, so the status changed to advertised. All right, which means now router 7 can choose the alternate path. All right. I did have to shut down the link on both sides. That's a little bit of probably a lazy design in my particular case, because we don't always have directly connected physical links to our eBGP peers. So if the local link stays up, we still may not have routing, and this condition would not work. I could, in that particular case, I could configure some sort of IPSLA, set up some sort of ICMP echo probe with IPSLA, and then I create a static placeholder route for that, and then I can conditionally track the placeholder to see if SLA fails, and then the route could be withdrawn, and then we can use the alternate path, right? The goal here, though, is to originate the network layer reachability information, but only do it based on specific conditions. In one of our future lessons, we're going to talk about another option, which is called conditional route injection. It also uses inject maps. It uses inject maps as opposed to the conditional checking. And it has to do basically with the opposite of route aggregation. The problem with aggregation is we're creating a shorter match and we're losing some of that network visibility. So for example, if I give you a /0 prefix, I'm going to send my you might send your traffic to me, but you may not be making the best decision on how to send that traffic. So in the cases where we're learning an aggregate, we may want to do some sort of traffic engineering based on longer match routing, and that's what conditional route injection is. But we're not going to talk about it tonight. For now, this concludes the end of this particular lesson. And hopefully you guys learned something. And if you have any questions, I'll go ahead and save the files. Let me go ahead and save. Well, I'll go ahead and save the files, but that's essentially the three options we talked about, right? Originating a route via network statement, originating a route via redistribution, or doing some sort of conditional advertisement to our peers based on specific conditions that we're going to match against. All right, so we'll wrap up this lesson. We'll see you guys tomorrow in our next lesson, which is where we're going to be talking about, what are we going to be talking about tomorrow? We are going to be talking about the best path selection process, which we've already done. I may skip this if it ends up being that it's kind of the same stuff that we talked about before, but the best path selection process can be a little bit confusing, so I guess it doesn't hurt to take a look at it again. All right, and then we're going to look into actually doing manipulation of individual attributes and manipulating route selection processes based on those individual attributes. Okay, so we'll see you guys in the next lesson.